if you have an interleave layout, you're going to have very densely, distributed, occupied, regions. And then when you come to here, some of the queues will be out of entries, right? So you could have more holes in your, in your memory. So when you think that you're actually writing the results into the block level queue, you are actually going to be accessing elements that are not consecutive to each other.
Right.
So this is also another reason why you don't want to have too many queues, because if you have too many queues, the distance here will be large, and then you almost guarantee to have these things to be in the same bank now. Okay, so that's why we usually don't have all the way up to 32 queues, because of, you have this kind of trade-off right here. Does that make sense? Okay, so it shouldn't make sense now, but then when you go home, when you have dinner, explain this to your roommate. Okay, and when you can explain that to your roommate, then you really got it. You'll never forget. Okay, so when you take the when the threads collaborate and write things into the block level queue, you would end up writing these strided elements from the shared memory into the consecutive locations in the block queue. But this is going to be coalesced, right? So that's how the real physical layout looks like. So we're almost there. For the hierarchy queue management, there are some advantage and some limitations. The technique can be applied to any inherent sequential data structure. This is great, okay? So if you have an inherent sequential data structure, you use these hierarchical queues, okay, to essentially to diffuse and to alleviate the contention, with a single queue. But the technique can be applied to any, the work level queues and the block level queues are limited by the capacity of shared memory. If we know the upper limit of the degree, we can adjust the number of threads or blocks accordingly. But this is also one of those dirty secrets in graph processing. There's certain graphs that are what we call the free, scale-free graphs, right? And some of the graphs have relatively uniform number of edges, right? Out of each node, but some of the graphs are highly skewed. So for Facebook, the Facebook graphs are highly skewed. The reason is, I have Wenmei Hu, and I have Angelina Jolie. Wenmei Hu, 2 neighbors. Angelina Jolie, 2 billion neighbors, right? So, there's no good way to characterize how many frontier nodes that you're going to be entering. So this is when a lot of the locality will start to break down. So whenever you have these highly skewed, graphs, most of these optimizations break down. Okay, and then you need to go into a different, very different regime. But that is actually very similar, if you think about it, to the short and fat, right? Short and fat sparse matrix, the kind of matrix modifications. Okay. Some of the entries are extremely long that you need to use a different method for the computation. Now, one quick thing, so that's the queue. So if we use hierarchical queue, and if we use these data layout tricks and so on, we can increase the bandwidth that we can, at which we can insert data into that sequential queue, and we create that kind of an illusion that the queue has a lot more bandwidth. However, there's a real limitation about this. The real limitation is that the operations that we're doing must be commutative and associative. So it doesn't matter when, as long as they belong in this, as long as all the queues, all the nodes in one frontier can be arbitrarily located in the queue, then our methods are good. So for breadth-first search, this is good. For the shortest path algorithms, this is not good, because which position in the queue you reside actually makes a difference. So you cannot use privatization for the shortest path algorithms. Okay, and that's one of the things that you need to be well aware of. And this is the reason why there are many papers published about breadth-first search algorithms, and there are very few papers published about shortest path algorithms. Okay, and pick the fight that you can win. Okay, so now let's go to one other issue about this. So this is the kind of the kernel arrangement. So remember, in between each frontier, you do have a barrier synchronization. Because within each frontier, we're using the same level, right? We're identifying all the nodes with the same level number, right? So if we accidentally process a node along with other nodes in the next level, we mix up the level numbers. So we need to make sure that we process all these nodes as level 2, and then generate all the next frontiers as level 3, right? And we need to make sure that we don't mix the two. So that's the barrier. And barriers are hard. Okay, barriers are expensive. So remember, if eventually we're using the global memory, the global queue, right? So with the global queue, in order for all the threads to see that next frontier that other threads have produced and so on, we need to terminate the kernel and then go into the next one. Okay? So, did I use up the balance? No? Okay. So we need to, we need to terminate the kernel and then launch another kernel to process the next frontier. And this is quite expensive. So we have some solutions. One is partially use GPU synchronization, or we can use a multi-layer kernel arrangement. So a very typical case is what we call the big kernel and small kernel approach. If you think about it, when you have if you have a very large number of nodes in a frontier, then the kernel launch overhead is probably tolerable, right? Because every time you launch a kernel, you process a large number of frontier nodes. So that's worthwhile. But at the beginning of your search, remember we start with the source node, right? And then you grow that frontier as you go to levels. So there will be several levels where your frontier is small. They grow, but they're still quite small until they grow to a big enough level, right? So for the first several iterations, you will be launching a kernel and do extremely small amount of work, and that's when it's not worth it. However, if the frontier is truly that small, they will fit in the shared memory, right? And also, when the frontier is small, you don't need to have multiple thread blocks to process them. So you may as well just use one thread block and just keep the queues in the shared memory as you iterate until you grow out of the shared memory, right? When you grow out of the shared memory, when the frontier is bigger than your shared memory, that's the signal where you need to go to the global queue. And that's when you launch a different kernel. So the first kernel will terminate at that point, and you start to launch one kernel for each iteration. So this is the small kernel, and this is the big kernel. And you oftentimes will see this kind of work in MPI code, in CUDA code. You will see these what they call the big function, small function, and they're essentially doing the same thing. The small functions deal with the situation where the amount of data is small, so they avoid some of the MPI the collectives and so on. And then when you get to the bigger data, then they start to use the real MPI collectives, right? Kernel. So for CUDA, it's the same thing. So this is the intro-kernel synchronization. And so for the small kernel, what you do is from level to level, you only propagate to the block level queue. You don't really go to you never go to the global queue. And then once you grow out of the block level queue, you launch the second kernel. And the second kernel will use the kernel relaunch, and then you would propagate the process. So another possibility is one can use the dynamic parallelism, and we have not introduced that. We're actually going to be talking about it. I just want to put a little pointer here. So when we talk about dynamic refinement, dynamic parallelism, and this, that will be one mechanism where you can that you can use to launch the new kernels from the kernel 1, and from the number of frontier grows beyond a threshold. Okay. So this brings us to the closure of these two lectures. Okay. And so now we're kind of we're in the I would call it the reality. When the data structure is very, very big, and then you're traversing the data structure, you're trying to search for certain values when you're trying to determine a path between one and another, and so you need to identify a subset of nodes to process in each step of the way. So then you start to look into these. You will start to look at these queues, and then you need to be very careful about the whether it's associative, whether it's commutative, and before you apply any of these techniques. And when you apply these techniques, there are a few things that you need to know. So once you know these things, it's actually quite straightforward to look at the high-performance library code. And you can easily just see, oh, so they're doing the warp level queue, they're doing the block level queue. But if you have no idea what the design is like, and when you go and see those libraries, they will mean nothing to you, right? So this is the reason why we teach these things. Once you learn the ones, when you look at some of the sophisticated MPI code and then CUDA code, they will all make sense. Okay, so this is the end of the privatization, but it's not quite the end of graph algorithms. So as part of the additional material this semester, we'll probably add at least one more graph topic, because these things are becoming more important. So we have learned some of the some of the graph analytics in the past few years. So we're going to try to add at least another sort of a more sophisticated graph analytics, so that to give you a better sense of how some of the graph analytic applications actually look like. Okay, so we would so I'll see you on Tuesday. So if you wanted to talk to me at the office hour, I was in the seminar, so just come by after class. Okay, see you.